Okay, welcome back to Operations Research, and we are now transforming a transportation problem into a nail so we can hit it with an LP hammer. And we actually found out the LP formulation. It was like this. And for this formulation, it's important to note that the C, that was a transportation costs, capital C matrix, is now somehow unfolded here as a vector. Okay, and then the supplies are here and demands are here. So it may be that these are not too difficult, but then note that the technology matrix that we have here, this looks rather intricate or complicated, or whatever adjective you want to use. And one important thing to note here is that there are only coefficients ones or zeros here. So it's a matrix of ones and zeros, which is kind of somehow easy. We only have to know where to put the ones and where to put the zeros, but that's the trick. And this is the trick we will show next. So next will be the solution. This spice must flow with highliners, and this is a quick and dirty solution. Quick and dirty meaning that we will look at this LP 9.3 and yes, solve it. And then we have a small, more elegant solution where we actually, build automatically this technology matrix A here. But let's go to the quick and dirty solution. So it is, as typical, we have a script M file that solves this problem. I call it highliner underscore QD for quick and dirty. So you can actually download it from here, and here is as it's listed. So again, at this point of your education, you should all be able to do this with GNU Octave. So I will not start GNU Octave now. I'll just go through this explanation. If you don't know how to download this and put it in your working directory and start GNU Octave and call the script there, look at the previous videos. I have shown this many times. Alright, so here is the contents of this highliner underscore qd.m file, and let's see a little bit what's going on here. So first, again, this is just a title block telling what's going on here. Then we have a data block. Let's go through this data block, which is of course more or less the beef later. Then we have how to solve this with GLPK, and then there is a commented a test result when I run it. And there is a little bit of explanation how this script M file works here. I will not, I will now basically say what is here slightly in slightly other words, since I'm not remembering what I wrote there. I go through this code and explain it that way. Probably I will be saying pretty much the same thing. So first we have the problem data, and actually this data, this is a two-part. So the first is just supplies, demands, and the cost matrix. S, D, and C. This is the data of any transportation problem basically. And what happens next? Next, what happens is that we transform this supply, demand, and cost data into objective vector technology matrix and bounds. So what happens next here is we build this LP model 9.3. So here is the C, And if you look at this, this is the matrix C here, capital C, but it's unfolded so that first we have a first row, and then the second row is actually not, it's taken there and put after the first row. So I think I call this unfolding. I don't know if this is a proper English term. But this is what happens here. And okay, so this is the, I think this is a pretty strange thing for you to look at. You haven't seen something like that. And well, to understand what's going on, maybe I kind of eat my words and start the octave. I mean, this is a typical thing. If there is some code and you don't understand how it actually works, well, try it out. And this is what we do now. We try it out. Let me try to fix the windows to a relatively nice size. So now I have octave here. I'm not actually in the correct directory now, but since I'm just trying things out on the console, it doesn't matter which directory I'm in. So what do we, oh yes, so what do we have here? So we have a C like this, and I'm doing a construct like that. What does it do? So let's try out. So Control L is clear the screen. So let me put the C to be what it is. So it's 3, 4, and 6 was the first row. Second row is 5, 7, 5. And I will not put the semicolon there. Let me check that it really is what it's supposed to be. 3, 4, 6, 3, 4, 6, and then 5, 7, 5. Yes, that's what it is. And what I want to have, sorry, that was a wrong, and that I also don't want to have. So I want to have C to be these coefficients here, 3, 4, 6, 5, 7, 5. So I want it to be the first row followed by the second row. And this can be done in many ways, of course. Almost everything can be done in many ways. But there is this kind of unfolding construct or operator, which is the colon. So we have seen this colon before also, but this is a weird use of it, which is actually very convenient now. So what this does, it takes in a matrix and then unfolds it as a vector. That's precisely what we want. So let's see what happens if I call C with just one column. So no, not that this would be the ith, these kind of things we have seen. So this fixes the first row, and this fixes the second column, and so on. We have seen this already. Then you might ask, what is this? So now both rows and columns run free. Well, obviously this is original matrix. Nothing happens here. Okay. So, but we had this C. Now let's look at what happens if we just do this. So technically, so far as we know, this should be a syntax error, but actually it's not. Something unfolding happened. So what happened is that, okay, so it took the first column here, 3, 5, then the second column 4, 7, it puts them after it, and then 6, 5. But this is almost what we want. Now it glued the columns after each other. We wanted it to actually glue the rows after each other. So the rows and columns goes the other way around that we want. But this is easy to fix. Let's just change the rows and columns of C by transposing it and do the same trick. So Now it's 3, 4, 6, 5, 7, 5. 3, 4, 6, 5, 7, 5. This is precisely what we wanted. So that's what happened here. So this was rather simple because we had this very nice unfolding operator colon. So now this is actually the third use we had of colon. And then comes the extremely tedious and nasty part, and it's this technology matrix. And for this, I think it's better for you to just train your eye. This is a matter of pattern recognition for you, really. So first we have supply constraints, and it means that we have these ones following zeros, and then zeros following ones, going in the way that we have here. Ones, then zeros, zeros, and ones. And if we had more supplies, then it would be ones followed by lots of zeros, then zeros, the same ones followed by zeros, and so on. So this block of ones would go to the other end of the table, and this table is filled with a lot of zeros depending how many we have here. But in this special case, so these are 3 ones, 3 zeros, 3 zeros, 3 ones. That's precisely what we have here. That is for the supplies. Then how do the demands go? So these are the rest here. And again, it's a matter of how you recognize here. I would recognize that we have first this block when there is an zeros and the diagonal, ones and the diagonal and zeros otherwise. So this is an identity matrix here, 3 by 3, followed by again an identity matrix, 3 by 3. So these three constraints, the demand side constraints, are in this formulation these two identity matrix blocks followed by each other. So these are the demand constraints for the destinations. Okay, so this is this part. That's the most complicated part, and in a general case it becomes even more complicated, of course, but this is a general picture, how it goes. What is the last part? Well, the last part is here we have the B's. So first we have the supplies, then we have the demands, and this is precisely what I did here. B is first supplies, then note the semicolon here, meaning that this will be the column vector S appended with the column vector D, so that this whole thing becomes a big column vector. So B is S semicolon D, and again I have always the semicolons in the end, so this semicolon means not the same as here. So here it means that there is a row change, and here it means that please be quiet. Okay, so now we have everything here. So we have C, A, and B. We can call the GLPK. Let's do it. So we ask the output parameter, so it's capital X now. That will be the optimal schedule. I use capital X because this should be a matrix. Of course, it will be a vector now, so there's a small price to pay, but in the end it will be a matrix. And cost is the schedule. So xopt, in this case xmin, and then zmin. I just use a capital X and cost for the names for it. Okay, normal call GLPK, CAB. Lower bounds are sign constraints, upper bounds are not there, so defaults there, nothing comes up. Then the next one, okay, here we have to think about it a little bit. So first two constraints, these are upper bounds because they are the source or supply constraints, UU. And then the demand constraints are lower bounds. These three are lower bounds, so LLL. And then a final thing, again, it's easy to make a mistake here. So how many variables do we have? We have 2 times 3. 6 variables. So there are 6 C's here. They are continuous variables, as we always have, almost always have continuous variables. So that basically solves it. Okay, now the solution, the slight problem here is that now this x will be a vector. And it will be a vector related to this C. Let's go back to Octave here. So we had this C. Why is it undefined? Okay, I didn't. So we had this C was like this. So the X, if we run this M file, will be a column vector of similar sort. So now we want to actually fold it back, if this is again the correct English word. So if we unfold it, matrix to a vector, then we want to fold back, or actually this is what is called reshaping. So you should look at the reshape help. What does this mean? So read that, please understand it, and the easiest way to understand it is, of course, try it out. So actually let us try it out. So we had the C capital like this, then we have a C like this. So we want to reshape this vector as a matrix. And let's try to do it. So here we have a reshape. So the first parameter of reshape is what we want to reshape. So now instead of the capital X, I use the C here. The C ij corresponds to xij, so it's pretty much the same thing is going on. So how do we reshape it? So it had two parameters. It's number of rows or number of columns. I never remember which way they go. It doesn't matter, because let me do it like this. It almost worked, except that the columns should be rows. Okay, maybe I could do this some other way, but now since it's almost correct, only rows and columns are switched around, so I use a transpose. And yes, I get back the original one. So this tells me that this reshaping, so I take the X that would be, after the GLPA call, a big column vector, I reshape it as a 2 times 3 matrix this way. And note that there is semicolon missing there, and also there is a semicolon missing there, so this means that this will print out the solution. And yes, indeed, it will print out the following. So highliner, quick and dirty. So the capital X will be 780, 10, 0, 10. And the cost will be 153. Okay, what does this mean? Well, it means that from source 1 to destination 1, 7 megatons will be transported. From source 1 to destination 2, 8. From source 1 to destination 3, 0, and so on. So these numbers here, I will, again, they are repeated here in this X, it will be like this. And for your convenience, I have written them down in this highliner spice transportation problem. So the problem is repeated here, and in the parentheses I put the optimal schedule. I mean, this is one way of representing this. So these numbers here in the parentheses are these numbers here. So this immediately tells us that, for example, from Tleilax to Kaitain, nothing is transported. From Tleilax to Gieri Prime, 10 megatons is transported, and so on. And the associated cost is, it's not written here, it was, okay, it's here, 155 billion solaris. So that was the solution of the problem, and a quick and dirty way of doing it. All right. Before going to the more elegant way of solving it, let's have our first exercise here related to this chapter, and there is a point that was true in this problem, but I kind of didn't state explicitly, so let me state it explicitly. So this problem, and now it's nice that we have this table here, so this highliner spice must flow problem and its solution are compactly here, except for the 155 billion Solaris. That's the optimal cost. Maybe I could use this space to put it there. Okay, but this is a balanced problem. What does it mean that the problem is balanced? What's the balance here? So if you look at the how much there is supply, what is total supply? So it's here. It's 15 plus 20. That's, I think it's 35 if I calculate it correctly. So here's what is the total demand. So it's 17 plus 10, 27 plus 8, which is 35. That's interesting. So the total supply and the total demand here is the same. So this problem is imbalanced, which of course means that if you think about it, I could have replaced these lower and upper bounds as inequalities, which is sometimes something that you should do. I mean, especially if you want to solve this by hand or use some special algorithm, this is a good thing that they are in balance, so this equality. In our general LP hammer, we don't really care. So it means that everything must be sent and everything is received. I mean, there is enough from the source side, there is so much, and demand side, there's an equal much demand. So all the spice must flow. Nothing is left in the sources, obviously. So this was a balanced problem. And now the question is, what happens in an imbalance problem? Of course, if the demand is bigger than the supply, the problem has no solution. How can you transport? How can you meet the demands if you don't have enough supply? I mean, this is clear. But there could be excess supply. So this is called excess spice. And yes, suppose now that there are actually 22 megatons of spice in Arrakis. So this 15 is turned into 22, so there is 7 megaton of excess supply. And the question is now, first question is, what is the optimal transportation schedule now? This, I think it's relatively straightforward. As a hint, yes, look at the solution above, highliner underscore quick and dirty. You can modify this. I don't think it's too difficult how to do that. You can also use the more elegant solution we will explain later if you wish. And then there is an additional question. What happens to the excess spice? So now there is 7 megaton excess. What happens to that? Alright, so that's the exercise 9.5. Let's have an exercise. Another one here, exercise 9.6. Again, we have the same problem of the spacing kill problem of transporting spice. The spice must flow with highliners. And something happened. So the route from Arrakis to Kaitain is blocked. I don't know, maybe there is some disturbance in the in the fold space or whatever. The point is that it is blocked. So again, if you look at this, so Arrakis Kaitain blockade. Arrakis Kaitain. This route from here to here, which we used in the optimal solution. So 8 megatons were transported here. Now we are not allowed to do it. We cannot do it. This route is blocked. What happens now? This is the question. And yes, well, hint is kind of, we have seen this before, and this is a very useful trick. So how do we interpret this as something here is blocked? So now this Arrakis Kaitain that used to cost 4 billion megatons is blocked. So in the solution, we must have 0 megatons going here. Well, very typical trick is if something is prohibited, something cannot be done. It's very difficult to tell this directly on LP. What we can do is actually to make this route so expensive that it will never be used. And now the classical way is the big M trick. So you put there a big M and then define the big M to be a big number. I mean something like 10 or 100 times bigger than any other number in the problem. And then because of that, if you look at the optimal solution, then there would be 0 here. And also, I haven't tried it out. I think it will work, but I'm not completely sure. Octave also calculates with these extended real numbers, so plus infinite minus infinite. They are also numbers, so maybe you can put there inf denoting infinity. Probably it will work. Okay, so those were the exercises, and we are still in the realm of quick and dirty solutions for transportation problems. So in the next video lecture, we will look at the more elegant or less quick and less dirty solutions for transportation problems. See you there. Bye.